Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on October 16, 2025, about 5 days ago. The standout result is that sparse memory fine-tuning learns new facts while slashing catastrophic forgetting. Natural questions F1 drops by 89% with full fine-tuning and 71% with LoRA, but only 11% with this approach at the same level of new knowledge. The paper is titled Continual Learning via Sparse Memory Fine-Tuning, and the implications for continual model training are quite significant. In short, the method updates only a tiny set of memory slots, chosen by a TF-IDF signal, preserves skills on tasks like GSM-8K and HelloSwag, and leverages memory layers that already access only a small slice of a million slot pool. Alright, the previous figure set up the motivation. Figure 1 illustrates the memory layer that replaces one feed-forward block with a memory lookup. Each token projects to a query that retrieves the top k equals 32 keys, so the layer touches only a tiny slice of a very large memory. The model then applies an input-dependent gate to a weighted sum of the corresponding values, which becomes the output passed onward. So Figure 1 laid out the lookup mechanics. Figure 2 shows how sparse memory fine-tuning selects what to update. The left panel counts which memory indices a batch actually touches across its tokens, producing a sparse access profile. The right panel ranks those counts against a pre-training background using TF-IDF, so indices that spike for the batch but were rare before rise to the top. Training then updates only that top set, while everything else stays frozen. So Figure 2 explained how indices are selected. This panel shows the trainable mask trick that lets gradients flow only to chosen memory slots while keeping the actual memory values unchanged during the forward pass. The equation enforces that only indices marked as trainable receive updates, which confines learning to a tiny subset. The note below adds that a forward pass may touch from 1,000 to 1 million indices, yet effective training works with t-set far lower than that. Well, that masking trick set the stage for selective updates. Figure 3 reports learning 1,000 single facts. The left panel shows trivia QAF1 climbing fastest for sparse memory fine-tuning, matching or beating the baselines. The middle panel shows natural questions F1 collapsing for LoRA and full fine-tuning, while both memory learning rate settings stay high, which signals minimal forgetting. The right panel plots GSM-8K negative log likelihood, which remains flat and low for memory updates but rises for the baselines. Well, Figure 3 showed single fact learning. Figure 4 shifts to document streams with top T equals 10,000. The left panel reports simple QA100F1 rising steadily, where memory updates match target performance while staying stable across learning rates. The middle panel shows natural questions F1 holding near its starting level for memory, while LoRA and full fine-tuning sync. The right panel tracks GSM-8K negative log likelihood, which stays low for memory, but climbs for the baselines. Alright, the previous figure contrasted document learning. Figure 5 shows the learning versus forgetting frontier, with horizontal axis as change in trivia QAF1, and vertical axis as change in HelloSwag accuracy. The teal memory points cluster to the right with values near zero forgetting, which indicates strong learning with minimal degradation. The orange LoRA and red full fine-tuning points sit lower, so higher capacity also brings more forgetting. Point sizes encode trainable parameters, and larger orange points tend to sink further. Okay, 2 takeaways stand out. Targeted updates to a tiny set of memory slots let the model learn new facts while keeping prior skills, and the TF-IDF selection plus masking gives a practical recipe for stable, continual training. The broader implication is scalable, low interference updates for deployed models. That is it for the AI Research Roundup. I am Alex. Thanks for listening.